So welcome Remi Locherer to the stage.
Yes, I'm Remi Locherer. I'm with Arista Networks and work there as a systems engineer. And the topic now is the TCP Authentication Option. I'm sure most of you are familiar with these couple of lines. It's a configuration for a BGP session. We're adding some policies. We add TTL security to the mix. And there is also a password to protect our adjacency, our BGP session. But there's a problem. This password is actually implemented using TCP MD5, which is a TCP option, which it was obsoleted a long time ago. And the following few minutes, we're spending on looking why we need something there and with what we're going to replace TCP MD5. So first, let's look at the challenge. We need to secure TCP sessions. And there are many actually well-known attacks on TCP session itself. For example, we can apply SYN flooding, which is a nice form of denial of service. Servers just keep the sessions open, but they will never actually complete the handshake, so they run out of resources. There are also TCP fin and reset attacks, which actually try to close an established session. We can also play with hijacking sessions, or replay attacks are also nice. How is your TCP stack reacting to that? I mentioned it's actually more or less well understood what attacks are there. So we have some countermeasures. For example, sync cookies are very well known, and in Linux, we use them since a long time. Also, some network operating systems have that on by default. Of course, EOS from Arista has it activated by default. We can also use IPsec to protect, but maybe it's if we just want to protect a TCP session from these attacks, it's maybe a bit too much. But it would protect it at the network layer, at the layer below. TLS. Well, with TLS on its own, we do not protect the TCP session. We protect the payload, but not the TCP session on its own. Then we have GTSM, which is actually a really simple measure with a big effect. So the sender sets the TTL in the IP header to 255, and the receiver rejects packets if the TTL is too low. But it does not protect eBGP sessions from an attacker that is just one hop away, like in an internet exchange, for example. And it does also not protect an iBGP session, which is most likely several hops away. And then we have TCP MD5, which actually tries to protect the TCP session through authentication. But it's based on a weak hashing algorithms, and it also has a drawback. Changing the key is really disruptive. If you use it with BGP, your session will go down. If you want to dive deeper into these attacks and countermeasures, they're discussed in this RFC 4953, which is already a couple of years old. Now, let's look at TCP Authentication Option, which brings to the table authentication for the TCP header, which is stronger and better than TCP MD5. We can use it to protect long-lived TCP connections. Typical applications are BGP sessions, but also LDP sessions. Or if you deploy RPKI, it would be well suited to protect the RPKI RTR session, which we run between a router and the validated cache. And there it will protect this TCP session from an attacker that tries to disable the session. And of course, it's one of the first sentences in the RFC. It obsoletes TCP MD5. It supports strong cryptographic algorithms and multiple of those. So if in 10 years we figure out, or even now we figure out, this algorithm is not good anymore, the protocol is built in a way so we can change that. We can add additional algorithms. It also provides key rollover functionality, so if we need to change a key, the session will not go down. And it provides replay protection. It's defined in actually 2 RFCs. The first describes the authentication option, and the second one describes the algorithms that are mandatory to implement it. Now, first, let's focus on the TCP header so that we see where this authentication option actually fits in. You see here, we have a source port, destination port, a sequence number, a couple of flags, data offsets that tells us where the data part, the payload begins, and there is this option field, which is optional. So you can send a TCP packet without it, or you can even add multiple options, but there's not too much space, it's just 320 bits. And in actually this field, in these few bits, we would place the authentication header. This authentication header first have a kind, which is actually an integer, which signifies what this header is about. So in the case of TCP AO, it's 29. And there is a length, because also the MAC, the authenticated hash that follows, depends on the algorithm. So we need a way to signal to let the TCP stack know how long that is. And we have a key ID to signal which key was used to calculate the MAC. And in addition, we can tell our peer, what key do I wish that you are using when sending something to me? And this is actually quite important, because this allows us to also change a key while a TCP session is established. I can signal, please use a different key for the communication. And then the rest of the TCP AO header is actually the MAC. And we're looking a bit deeper how this is being calculated. Let's look at a couple of concepts how this is set up. So one important thing is what is called master key tuple, or MKT, which is usually referenced. It consists of a connection identifier, which is like IP address, port, source, and destination. There's a TCP option flag, which signals if you want to include all other TCP options in the calculations or not. IDs to signal which keys. And master key, which is, if you configure it by hand, is the string that we type into the config to use as a key. Then an algorithm that we use to actually create the key that is being used, and the message authentication code, which is a cryptographic secured hash. One of the properties is, once this is set, we should not change it, or at least while it's in use for a given session, but we can add new MKTs. And we can update or change the MKTs that are in use for a given session. Then we have traffic keys. This is the actual key that is then used to generate the protection to create the MAC. Kind of as input, we have the master key, which we looked at before. We have local and remote IP address pairs, TCP port numbers, and the initial sequence numbers. That also means the keys are unidirectional because of the port numbers that we hash in. And it has another impact. Since we include the ISN, the initial sequence numbers, when we send the first SYN, we do not know what the peer will be using. So that means we generate, for a given session, 4 traffic keys, but most likely we're just going to use 3 of them. And the second RFC I mentioned before mandates that we implement an HMAC based on SHA-1, and a second algorithm based on AES 128. And now the next part is, now we have all the keys and know how to generate and use them, but now we need to actually do something with it. So again, here we have two algorithms that are mandated by the respective RFC. And we use these algorithms to calculate the secured hash while using this key, an IP pseudo-header, because you don't want to have stuff like TTL, which changes in the calculation, the TCP header, and of course the data. A very interesting concept here, we add a SNE, or a sequence number extension. This brings us replay protection. What is the issue? A sequence number in TCP is just 32 bits long. And for a long-standing session, that's actually what we want to protect. You can have a rollover. And so that means in a long-standing session, the same SNI will appear again. TCP AO adds another 32 bits at the upper layer, and every time we have a rollover, calculates one up. So this gives us replay protection. Once we have a rollover of the regular sequence number, we're still protected. So that's how the protocol works, but how do we actually use it? In this configuration snippet, we see that we define something like a key chain, which is here called a shared secret profile. And we can define several keys. And they are identified with a number. Here it's secret 10 and secret 0. And these are actually the IDs that you see in the header or reference with key IDs. So there we have the exact match from what we have in the config and what will be in the TCP header on the wire. Each of these keys, we can add a lifetime. How long do we want to use this key to transmit data? And also, how long should it be valid to receive data? So both directions can be defined. And the operating system, or the TCP IP stack, is then choosing, at least in the case of EOS, the kind of the youngest valid key to actually send data. And then once we have defined these keys, we connect it in the part of the BGP neighbor configuration. We connect with that profile, and we define which algorithm should be used. If you go to this website, to GitHub TCP AO, you will find many examples of other vendors, and also some tests are published there, how they interact and if they actually work together. So if you want to start with TCP AO, this is, I think, is a good starting point to look at some configs and learn how it all works. So, but where is it actually implemented? Is it available? Can you use it today? Well, you can. Many networking vendors implemented it in their software. It's not 10 years ago that they did so, but in the last couple of years, many did. I'm sure there are also others. I just did not maybe Google good enough for that. But there are probably others. But I think the major vendors are available here. In our debugging tools, it's also available. So if you use TCP dump or you use Wireshark, you can see all the flags in the TCP AO header and can use that to debug if there is an issue. But the situation is a bit different if you look at open source kernels and implementations there. In the operating systems I know, it's not available yet. There is a Linux patch by Leonard, which is still discussed and worked on, but is not in the mainline Linux kernel. There is a second patch set, which is being discussed by Dmitry, and he actually works on the initiative to upstream the Arista TCP AO implementation into mainline Linux kernel. The difference to the patch from Leonardo from an architectural point of view is the keys in the kernel are just per socket, and we do not have a centralized key database in the kernel. That's then the job, for example, of a BGP implementation to provide the socket with the right keying material. And then there is a FreeBSD patch by Philip. He started in 2021, then it stalled, and he told me that he most likely continues in the future with his work of TCP AO implementation for FreeBSD. So the impact of the kernels not supporting it today with freely available, or not out of the box at least, I mean patches are available, is it's not present in open source routing stacks. This is a feature request from the FRR repository. Someone asked for the feature, and Donald Sharp replied, well, first it should be available in the Linux kernel, and then we do it. And actually it makes sense, because if the API changed after you implemented it, or how should you test it if it's not supported by the operating system? So it's actually important that we get this implementation into the Linux kernel, into the BSD kernel, so that we can actually widen the ecosystem. So what are the main takeaways from the past couple of minutes? So TCP AO is there to obsolete the TCP MD5 option. According to the RFC, this happened more than 10 years ago, but there we are. It supports strong cryptographic algorithms. Very nice properties. It allows rekeying during an existing TCP connections. We've seen that it is supported by many networking vendors, but there's no support yet in Linux and BSD kernels. I hope this was informative for you. And I recommend that you go and check your equipment if it's available for you. Thank you.
Thank you.
I'm Simon Leinen, Switch. It's not a question, but a comment. Thanks for the talk. I agree, it should be in the Linux kernel. Wonder why it has managed to not be adopted in the time it exists. But it is not true that no open source routing software supports it, because FreeRouter, not FRR, does implement it, because it has its own user space TCP implementation, and someone added AO to it.
Didn't know about that. Thank you.
Do we have an idea on how many attacks can be avoided using this kind of authentication?
Well, I do not have a number. I did not any research. The attacks will not be super high, because you see there is a not too big space where it actually helps and makes sense. So in many cases, if you just have a direct peering, you can protect your BGP session with GTSM, and that will be sufficient if just 2 routers are on that link. So my expectation is the number is not in the millions.
Yeah. I have another question. Sarin from Ost. I think it's a very important and interesting topic. So you talked about replacing MD5. And then you talked a lot about SHA-1, which was at this time the draft was written in 2010. They said, yeah, okay, it should be enough for a few years or for the next years. And I think we had the first collision attack around 2017. So how do you see will this draft be at some point replaced soon with really other algorithms, which seems to be secure for also the next years? Because I think right now SHA-1 is not the way to go for the future.
Well, multiple things to this. First, yes, it's a couple of years ago. If this would be defined today, this RFC, it's probably not SHA-1. That is one of the candidates. But even now, with the RFC, you have a stronger, a better version with the one based on AES 128. And there are already implementations of stronger ciphers. But what I also want to highlight, even though if you use a hash, just as a regular hashing algorithm, SHA-1 is probably not appropriate anymore. In the case of a Mac, situation is not as bad. So, but if you deploy now, maybe you use the stronger available option and not the SHA-1.
Okay, perfect, thanks.
Hi, Remi. Did you check some firewall vendors as well, if they are going to implement this option? Did you do any research?
I quickly browsed through some documentation of the well-known firewall vendors, but didn't see it. But I must say I did not call them or did super deep research. So it's possible that I've overseen one.
Actually, a question regarding the algorithm itself. You mentioned that it's using an IP pseudo header. Like, do you know why that is? Because it doesn't really make sense to me, since we're protecting.
So it's not using the full IP header to put into the calculation, because there are some fields in the header that are legitimately changed while it travels. So the receiver and the sender will not have exactly the same. For example, TTL.
Yeah, but why does it even use the IP header, like, at all?
Because there we have the certain destination IP address, which is relevant to identify a TCP session.
But is it relevant to calculate the MAC itself?
Yes, it is relevant because otherwise it's not tied to this TCP session.
Oh, yeah, makes sense. My fault.
And it's actually also that if you have an additional TCP session, even if it's between the same two hosts with the same IP address, you will have new traffic keys for that.
Any more questions? Okay, thank you very much, Remi.
Thank you.